So thanks for joining me to listen to my lecture 5.3 regarding the Lorentz model of an atom and essentially an electron. And I would say that this is the most important lecture of this week. So please stay tuned on what I will be saying here during these 50 minutes or 40 minutes or so. So motivation for this lecture and the Lorentz model is that it's a classical, easy model to understand, and it really provides us a very good understanding already of the refractive index profile that are associated with most of dielectric structures, dielectric materials, and it really provides us a good physical understanding of how come we have these kind of refractive index profiles for the materials. And then putting things into a context of optics, dielectric materials, essentially we are thinking now, for example, the materials for lenses, so different kinds of glasses. We can even think of different waveguiding materials, again, basically glasses, or we can think of different semiconductor structures and materials. So one can, for example, think of integrated photonics and then integrated photonic circuits. There, silicon, germanium, gallium arsenide. So these semiconducting structures and materials, they essentially are also having a quite a specific refractive index profile. So with semiconductors, essentially what I'm trying to say here is that their refractive indices are quite high, so way above 2. And this is something that we can, after this lecture, understand that how come semiconductors have such high refractive indices and how come they are higher than with typical dielectric structures and materials. And this is my brief motivation for this lecture. So this is very important in terms of optical materials, and in the end it always boils down into using some materials when we're actually making things applied. So when in applications, it's always the case that we're actually using some kind of realistic materials. And there, it's the refractive index and the dispersion of the refractive index that is the key for forward. So, like I said, Lorentz model, this is our main topic of this lecture. It's a classical model, so we don't treat quantum mechanics here. And what we aim to achieve and we can do after introduction of this model is that we can qualitatively understand and even partially quantitatively the light-matter interaction taking place in a macroscopic scale. And what we want to do here is that we want to form an intuitive, so that the model that we can understand how things work out and it has some predictive power. And we want the model to be microscopic so that we could also, in a way, think what kind of possible changes on the microscopic scale, on the atom scale, would do to change the properties of the materials. And this, in the end, we aim to achieve that we can actually qualitatively predict and calculate the refractive index profiles of different materials. And here, why I'm saying profile, I'm really meaning dispersion of the refractive index. So essentially not just a given single number for the refractive index n, but rather how it depends on the incident wavelength. And the model we will be introducing is known as the Lorentz model for an atom. Maybe a misnomer, since mainly it's the electron residing nearby the atom, bound to the atom, oscillating by the incident driving field that actually causes things. But nevertheless, this is the name. And it applies very well for dielectric materials. So different kinds of glasses, for example, or silicon nitride would be another example, or magnesium fluoride, and these things would be example materials. It works okay, so tolerably well for semiconductors. And here I would say that the approach would be that we need to generalize things a bit. Mainly, I will spoil you the fun. We will need to change the mass of an electron bound to the atom with the effective mass. And the effective mass is a concept that arises from the periodic structure of the material. And this is particularly important in semiconductors. So it's really the electronic band structure that dictates effectively how massive the electron or hole is that is oscillating inside the material. So this is how we should generalize things. Also in semiconductors, if you would want to generalize things further and to be more quantitative, especially if you would go to longer wavelength regime, we should also take into account emergent phenomena arising from the periodicity of the semiconducting material. So essentially, we should, for example, try to look into the phonons and other collective excitations taking place inside the material, so that those kind of things should be taken into consideration if we would want to calculate the refractive index profiles, especially at the longer wavelengths, so at the infrared wavelengths. But mostly for the optical wavelengths, even with the semiconductors, we can do by just changing the mass into an effective mass. So my main point is already written here, so it works reasonably well for semiconductors, and let's be happy with that. Where this model fails epically, it's in the case of metals, and here I would like to highlight to you that it's the Drude model that works quite well. And in case you're not familiar with the Drude model, it's essentially a free electron model, or can be extended, also be a nearly free electron model that provides a better framework. So how electrons respond in a metallic material. And more about the Drude model, of course, in our follow-up courses, or maybe you have already taken this structure of matter. Like, I think we are speaking a little bit about the Drude model and the response of metals. And then, of course, in the course of solid-state physics, we will be dealing more with the Drude model. So this is for you to point out, for you to acknowledge where we will be treating this extension, or we could extend our materials to also be suitable for metals. But the good rule of thumb here, since we are focusing on optics, is that with metals, light doesn't really propagate much inside metals. So in fact, we can just be happy with the notion that metals are materials that are not of interest in terms of light being propagating inside the material. We can make good mirrors with metals, we can make wave-guiding structures with metals, but light doesn't really propagate inside the bulk piece of a metal. So that's why we don't really need to also understand their properties that much in this framework. We can just think that we're happy in equating metal as a perfect electric conductor, and then we can equate that as a mirror material. So everything of light is being reflected at the very surface of the metal. Okay, now we get started with the introduction of the actual model. And what do we do in this Lorentz model is that we consider an electron, and we assume that is attached to the atom by a and the atom, of course, is associated with a massive core, so that the mass of our atom's core is very much larger than the mass of an electron. And we assume that this electron is attached to the core via a harmonic spring. And the spring constant of the spring is denoted with K. Please do not mix this with the, for example, wave number, but this should be fine. And of course, K is often the often used term in Hooke's law describing action of a spring. So that's why I felt that it's better to use this terminology here. And this is a schematic explaining what happens. So here we have with a positively charged nucleus, so the atomic core, and then we have this single electron attached into the massive core with a harmonic spring. And harmonic just meaning that it has just linear dependence on the force with respect to the displacement from the equilibrium position. And displacement here is denoted with x. So here we have a single electron, and here we have a massive core. And when we are dealing with linear optics, and we are dealing with a situation that the electrons are not strongly coupled to each other, so we are not dealing with collective excitations and whatnot, this is just fine. So just imagine that even though we have many atoms in our bulk material, they don't see each other, and we're just happy in looking into the response of a single electron. And at the end of the calculation, once we know how a single electron behaves, we just multiply that roughly with an Avogadro's number to get the kind of overall response of all the electrons present in the material. So this is the trick we do. So we do not think how atoms, we assume that the atoms and the electrons don't really interact with each other. And this is most of the time a pretty good approximation. Okay, in reality, of course, we don't have a spring inside atoms. So what binds electron into the core is first of all electrostatic forces and Pauli exclusion principle. So the electrostatic forces basically bind the electron into the atom. So like we see that here we have negative charge, we have positive charge, so that they are being attracted to each other, so that due to the electrostatic forces, the electron would want to go nearby the atom, and then the Pauli exclusion principle essentially then forbids the electron to come here nearby. So we will have some kind of electrons also nearby the core, and due to the nature of electrons being fermions, then the Pauli exclusion kicks in and forbids those lone electrons, the conduction electrons or valence electrons at the outer shells of the electron structure to go and collapsing into the atomic nucleus, into the core. So this is what happens, and this is how things work out in reality. So we don't really have a spring, but the spring concept works quite well, so let's use it. And for conceptual clarity and for peace of mind in terms of the mathematics, we restrict our treatment to a one-dimensional case. So essentially we just think that we are displacing the electron in a single direction, and here we denote that it's the x direction. And this is actually an approximation, an assumption that applies very well when we have an isotropic media. So then we don't really need to deal with the kind of fact that what would happen if the electron would be displaced in a different direction. For example, if we change the polarization of incident light. So this is fine for us, and we just justify this assumption by just stating that, most of the optical materials out there and of interest to us in the framework of this course are isotropic. For example, if you just have a bulk glass, all the different glasses that we could use to form a lens, then those are isotropic most of the time. Well, in reality, they are not. They're actually birefringent, but just be content with this approximation and assumption. And of course, this helps us in the mathematical treatment, because we can really then just use scalar quantities, and we would not need to use vectors and tensors to describe things. But if you're really interested about this, don't worry. In the follow-up courses, we will extend this. So especially in the optical systems and beam propagation course, it's a great course. We will extend Lorentz model into anisotropic media. So there we can fully understand how we can, for example, have birefringent materials and such. So birefringent materials, which means that depending on the direction of incident light and on the polarization of incident light, the refractive index is slightly different. And many real materials actually are birefringent. So please be warned that life is not this simple as we are treating here on this lecture. Okay, so what we do here, we further assume that the electron is being displaced. So it's being moved around, and it's being moved by a presence of having a time harmonic plane wave E field here that is causing the electron to be in some motion. So here essentially we have the E field, and this is the driving field, so it's putting the electron into an oscillatory motion. So essentially that's the field that puts things into motion, breaks the equilibrium of situation. And since we say that we assume that this is time harmonic plane wave, the E field will be a form that we have the field amplitude E0 times the exponent I omega t. We don't really need to be thinking about the spatial dependence of the field, the wavelength of incident light. We are speaking of optical wavelengths, and the electron will be moving only of the order of few angstroms, so that then we don't really need to worry about the fact that it would not be or the field amplitude would be changing, so that we don't need to deal with propagation effects here. And this field causes a force to an electron, of course, due to the fact that the Lorentz force equation still applies, and the force is equal Fe, so E as a sub-index of denoting that it's caused by the electric field, and this is essentially Q times E, where Q is the charge of our electron. So Q times E naught times the exponent of I omega t. So please recall Lorentz force, which in a vectorial form was that we have the vector force equals to Q, the charge of our particle feeling the force and the fields, times E plus Q times V with the cross product of the magnetic field. So this is the Lorentz force law. And we are just basically applying this, and we forget the fact that even in the case of an electromagnetic radiation, we would have a non-zero B field here. So in addition of just being displacement along the direction of the driving field, we would also put the electron slightly into a kind of circular path. But this is what we forget for now. Maybe in a follow-up, you can have a homework, like looking into these effects and seeing how that could be related, for example, a optical activity of materials. So this force displaces the electron, and the equilibrium position, we denote that that's x equals 0. And now we have the spring force F equals minus kx. So this is just Hooke's law applied into our situation. F equals minus kx, and this is another force that the electron is feeling. And now we want to understand the dynamics of the electron, because that then gives us the response of our material. So we must look into the motion of the electron. And of course we can use the classical Newtonian mechanics, and we can write an equation of motion for the electron. And at the end of this writing up, we have F times A. So basically the second time derivative of displacement equals the acceleration. So F equals ma, Newton's law. Then we have the Hooke's law, so we have the spring force minus kx here, and this is the second force, and then we have the driving force q times E naught times exponent minus omega t. So essentially you are just writing an equation of motion, and that's, as the name suggests, is an equation that describes how the electron responds with respect to the driving fields. And then we have applied F equals ma, and the sum of forces being equal to 0 to write the equation of motion. Here, m is the mass of an electron, and the notation x with 2 dots above it just means that it's the second partial time derivative of the displacement x. This is just the notion. For semiconductors, like I already said, we can generalize this model for semiconductors quite well when we replace the mass of an electron with the effective mass of a conduction electron or a hole. But more on that in the follow-up courses. How come this kind of concept of effective mass actually arises? And in a nutshell, it arises from the electronic structure of the matter. And for semiconductors, this actually plays quite a bit of a role in the response of the material. And now we can solve the equation, and we can solve it into a form that on the left hand side we only have the second partial time derivative of the displacement plus omega naught z squared times x, the displacement, equals q times E naught divided by the mass. So we have essentially just divided both sides of the equation with the mass, and then we have the time dependence of the driving field. So we have a time harmonic field driving the electron motion. The omega naught here is essentially the square root of the spring constant k divided with the mass. And now we see that the things make sense. And this is actually, in fact, a resonance frequency of my harmonic oscillator. So if I happen to drive my harmonic oscillator with this frequency or nearby this frequency, the oscillations actually are quite strong. And if I'm far out, then the electron doesn't really feel much of the driving field. So that's the meaning of a resonance frequency in these kind of systems. And we can easily solve this trial function. So we have a simple differential equation, and a physicist, most of the time, we just solve differential equations by just using a trial that we know is a solution of these differential equations. So we use a trial function of x. So this x, of course, is our displacement. And as the figure shows here, essentially x tells us how far the electron is from the equilibrium position, where the electron would be when there is no driving field. So now x as a function of t is telling us how the electron oscillates with respect to the equilibrium position. And the trial function is of form x naught, some maximum displacement of the electron times time harmonic time dependence exponent minus omega t. And we put this into the differential equation, and of course we can calculate things and see what kind of condition arises for this maximum displacement for the electron, so x naught. So the first term turns into a omega squared times x naught times time dependence term plus omega naught squared times x naught times exponent I omega t. And then we have on the right hand side, we have the q times E naught divided by the mass of the electron times the time dependence. And we can see now that all these terms, we have the same kind of time dependence, so that we can we can remove them. And then we are left with an equation that we have the squares of the frequency, so omega naught squared minus omega squared multiplied with x naught times q times E naught divided by m, the mass of the electron. And we solve this with respect to the x naught, so the maximum displacement, so that we see what kind of condition we have for this amplitude for the electron oscillation. So that's of course, the maximum displacement the electron has. So that will be q divided by m divided by omega naught squared minus omega squared times E naught. That's the amplitude of the driving field. And now we can plug this into the trial solution, and we can see that the time dependence of the displacement is of a form that we have some kind of magnitude term depending on the driving field's frequency, how close we are to the resonance frequency omega naught, and then we have just normal time harmonic time dependence. We can shuffle things around so that we have a slightly easier way of describing the displacement, simply that we have some kind of amplitude term here depending on the frequency difference. So when we are close to the resonance frequency, this guy at the denominator, of course, skyrockets, makes the amplitude term to skyrocket high, and then we have the time dependence of the driving field. So this is our result. So we have solved the system for the Lorentz model, the equation of motions, and what it tells us now is that this oscillation or displacement of the electron really follows the optical driving field. And since we know that the speed of the driving field, we're speaking about optical fields driving the motion of the electrons, is that this oscillation is actually quite fast. The amplitude of the electron's displacement also is seen to depend on the frequency difference, so this term omega naught minus omega squared. And essentially this means to us that the amplitude increases when we are close by to the resonance. Depends also linearly on the amplitude of the field, so E naught, and this is good to know, so that the kind of displacement behaves in a very simple manner with respect to the driving field. And let's now use this model to try to estimate what kind of refractive index of n we have for a given medium of interest. And especially we want to understand what kind of dispersion the refractive index profile has. So what will be its frequency dependence or wavelength dependence. And how do we start? Is that we start by thinking that we want to understand how a single electron behaves, and then we scale up this understanding into the macroscopic scale, since we can estimate how many electrons we have in a piece of a material, so that this will be our approach. And we forget the possibilities that the electrons somehow would see each other. So we start with the dipole moment small p and describe the medion's microscopic response using dipole moments. And when the system is at rest, so there's no driving field, this atom electron oscillator system has a zero dipole moment. So it doesn't oscillate. And here what we do is that we assume that the motion of the electron gives rise to the dipole moment is of form that the dipole moment is q, the charge of the particle, times the displacement. And then here we are thinking of the dipole moment formed by an electron. So this is the charge here will be the charge of an electron. And the material polarization, and this is now the macroscopic quantity of interest, and we denote this with the capital P. We just think that this is now easily calculated, that once we know how many of these dipole moments we have per unit volume, so we can multiply then the individual dipole moments response with this density of dipole moments, and we get the material polarization. And now we plug in things, and we have the q squared times n divided by m, divided with the omega naught squared minus omega. And then we have the time dependence of here. And this is actually quite nice because it looks familiar with respect to the kind of macroscopic equations we came up with for the material polarization, and they always had this kind of linear time dependence. So in that sense, things look okay for now. And now, like remembering that the macroscopic material polarization P can also be described, that it's the dielectric constant epsilon minus the dielectric constant of vacuum times E, and then we can combine these together, and then we can actually write an equation based on the Lorentz model for the dielectric constant of the material. And now, since we do have this frequency dependence in our equations here, we can even in fact state that now we even have a material response, dielectric constant, and we can write it as a function of the driving field's frequency. So we have the epsilon, and that will be epsilon naught plus a term arising basically from the Lorentz model. So q squared times n divided by m, and the frequency terms. And the refractive index n, of course, we can find it that easily by just recalling the equations derived in the previous chapter. So that the refractive index, in the case when we do not need to consider the magnetic properties of the material, and this is really a very good approximation at the optical wavelengths, and especially for dielectric materials, so that the refractive index is essentially the square root of the dielectric constant epsilon divided with the vacuum permittivity epsilon naught. And here essentially we can now write that the n squared is 1 plus n times q squared divided by the vacuum permittivity epsilon naught times the mass of the electron times 1 over resonance frequency of the system omega naught squared minus omega squared, and omega here is the driving field frequency. So this is now a formula equation we have found for a dielectric, and the nice thing here is that in fact we actually can even describe the dispersion of the refraction of a refractive index, and that's the main thing we want to achieve here. So let's now look at the implications of these equations, and this one equation we have derived. So when we are far away from the resonance, so essentially when the driving field's frequency omega is way smaller than the resonance frequency of the system omega naught, what we get out from this model is that the refractive index is larger than 1, and it's almost a constant valued number. And this is fine. This is good. We know that the materials, we should have a refractive index that is larger than unity, so that the speed of light in materials is not higher than the speed of light in vacuum, and almost a constant valued refractive index profile is something that we do see with most of the dielectric materials. When optical frequency is above this oscillator resonance frequency omega naught, so mathematically when omega is larger than omega naught, the trouble is that now the refractive index would be smaller than unity, and well, in some cases this is what seems to be the case, especially with metals nearby their resonance frequencies, so that in principle this is okay. We are not breaking any laws of physics here, but the thing here is that the light doesn't really like to propagate inside such materials. So metals would be the case, and the UV wavelengths would be the wavelengths of interest if you would want to see this kind of physics. And the kind of difference would be that the refractive index would be, the real part would be like 0.98 or something. So it's only slightly less than unity. And it arises from the fact that we actually have a lossy system. So this is the kind of downside. Or a kind of thing, a sanity check that ensures that physics, the kind of main laws of physics, are still being complied with what we have done here, so that we do not break the speed of light with our math. The problems here in this simple model that really arise is that when we would be exactly at the resonance frequency, so when omega equals omega naught, And what would happen there is that the refractive index skyrockets, so it really approaches infinity, and this is really unphysical and disagrees with all the experimental observations that the mankind has made. So because it's really hard to come up with materials that have a high refractive index profile. Like the kind of high refractive index profiles are of the order of for example, 3 or 4 or slightly higher if you really go into exotic materials, but never can we find materials where the refractive index really goes closer to the infinity. So this is somehow against what we have seen to be, what seems to be the case in nature. So we should really improve the model and think what is the kind of main thing that is now making our simple model unphysical in practice. And this is what we will do in the latter part of our lecture. The problem of the model is that with the spring system we have come up with, it's essentially a lossless spring system. This has many physical implications, what this actually means, but one thing that we can look at this, or one point of view we can look at this, is that the lifetime of the resonance, so the tau, becomes infinitely long. So once we have put the electron into motion, it oscillates for infinitely long. There's essentially no losses in the spring system, and this is something that is not physical. So in a realistic system, the electrons actually are quite lossy, and the spring system is quite lossy, so that when we are putting electrons into motion inside a bulk piece of a material, it doesn't take that long for them to actually relax back into the equilibrium position. So definitely we must incorporate losses into the system somehow. And this can be easily done when we add a damping term into the equation of motion. So essentially, like we add a term into our equation of motion. So we add this kind of term there. We have mass of the electron times gamma, and gamma is a damping term, times displacement of the electron, and the first time derivative of that. Plus, we still have the Hooke's law, so we have the damping or driving caused by the spring, a kx term, and then we have the driving field caused by the incident electromagnetic radiation. So we essentially now have just added a single damping term into the equation of motion, and we now want to solve the equation and see if the problem is solved. And of course, again, we use a trial function, and ultimately we do not do the derivation here. We have a refractive index profile squared that will be of form that n squared is 1 plus n times q squared divided by vacuum permittivity epsilon naught times mass. And then we have the same term as before for the frequency differences, plus a new term minus I here is the imaginary unit, times gamma, the damping term, times omega. And this is a new term that we did not have before. And this is actually the key for improvement. Now let's get forward. So we have this equation that we just did not derive, but I just showed you. And here the kind of physics that comes along with this extension of the model is that now we have the derived refractive index profile. And here, as we can see, we have the I there. This refractive index is a complex valued function. And we do not do this derivation or like a showing of these two bullet points, but basically we can easily show by just letting a field to propagate in this kind of material where we have a complex valued refractive index, that the imaginary part of the refractive index of the basically corresponds to absorption. So that makes the system lossy in practice, so that the field does not propagate anymore indefinitely long inside this kind of material, but rather it starts being decaying due to absorption. And then it's the real part of the refractive index that is related to the oscillation of the electrons, so essentially into that displacement. And this term, this real part, can be associated with the propagation velocity for light inside this medium. And since the refractive index was defined, that it's the real part of the refractive index is being defined, that it's the propagation velocity v for light divided with the speed of light, or the other way around. So we see that the things make, again, sense. And now let's now look what this implies for the actual light-matter interactions. So the Lorentz model that we have now introduced to you, it really explains the most important concepts that we need regarding light-matter interaction. So we can qualitatively calculate the refractive index profile, and we even can predict and estimate what would be the wavelength dependence or frequency dependence of the refractive index. So essentially, how the refractive index is dispersive. The trouble here is that in itself, it's qualitative, that we cannot really use it to quantitatively describe different refractive indices, even in the case of different dielectric materials. So this is the problem that we are facing here. So it's a qualitative model that it doesn't have that much of good quantitative predictive power. But the good thing is that it does provide us a good physical insight that what are the kind of microscopic physical origins that give rise to refractive index and changes in the refractive indices when we go to different materials, and most importantly, how come refractive index profiles are dispersive. And why this model is not quantitative, like in real materials, of course. Essentially, their properties, how the electrons behave, their responses are really dictated by the electronic band structure, and this applies in practice. So we should really go into a full quantum mechanical treatment. We should look into periodic materials, that what happens when the atoms and the electrons actually are in a periodic structure, and those things will change our treatment. So basically, the periodicity of our material gives rise to the electronic band structure, because the electrons are fermions, and then based on that, we should really change the model. So we should take into account the quantum mechanical treatment of the problem and essentially the periodic nature of the matter. So this is how we should generalize, but here we are not interested. We're rather interested in kind of main bits of terminology and to basically understand what gives rise to the dispersion of the refractive index profiles. And in practice, and this is always the case with any materials, we have an infinitely many resonances, and so far we have only considered a single resonance playing a role in the light-matter interaction. And this, of course, should be taken into account when we would generalize our math, so that we should really take into account that we have many resonances, and the kind of probabilities of exciting these resonances with incident light depends on the cross-sections of these excitations. And of course, if we would want to really calculate these cross-sections, we should apply quantum mechanics in a good way to estimate things. But this is not our main point in this course, so we just leave it for the follow-up studies. We just briefly generalize the model into dielectric materials where we can have several resonances. So I do not derive this. I just say that how we could generalize, and what happens is that we get a better agreement with actually measured refractive index profiles. But here we are essentially more instead of calculating from first principles ab initio the refractive index profiles, we are rather just fitting a model based on this simple model on the measured refractive indices, and that then would give us a kind of prediction of the refractive index that we can use in the future. So, how do we extend into several resonances is that we assume that each of these resonances, and each of those would correspond essentially to a different electron transition between the energy states I and K. We assume that these resonances interaction cross-section, so we denote that a sigma j, is proportional to Fj, where F is essentially a kind of normalization constant. And resonance frequency is also playing a role here. So that each of these resonances have a different resonance frequency. So instead of omega naught, we must also generalize them to be several resonances. And now we should also plug in different damping terms, gamma j's, so that we could actually write the equations of motion in this case. So here we just assume that if we would be able to calculate these terms, so that if we would be able to calculate the damping term of each resonance and the kind of interaction cross sections of each resonances, we could in principle then calculate what would be the real refractive index profile. And now we could use an equation, and I do not derive this, I'm just showing how things would be generalized. We have very familiar beginning, 1 plus something nq squared divided by epsilon naught times m, and then we sum over these kind of frequency terms where we each of them arises from different resonator. So different resonances in the material system. So this looks very familiar as before, and we are here we have this kind of a normalization constant Fj that they ensures that depending on the number of resonances, everything still looks okay, so that things doesn't explode. So if essentially the normalization constant Fj or constants Fj are being defined, that in the end their sum will be unity, so that in a way something at least happens. So this is how we could generalize refractive index into many resonances, and in fact this equation has been used quite a bit in the history and is known as the Helmholtz-Kettler equation. It also has many other names, but this is maybe the most known. And this would be the kind of most general equation for the refractive index in the framework of this course. And it shows us that now, depending on the material, we may have different kind of resonances with the material. We do not deal with the question of how we could calculate where these resonances all are and how strong they are, but we're just happy in thinking that different materials, they may have different resonances, and subsequently the refractive indices of the different materials will be slightly different. So at least conceptually, this equation provides us a pretty good understanding of physics. So this is the equation. And finally, I would just like to point out what kind of physics we get out by utilizing this kind of equation. So we just sketch what kind of refractive index profiles we have when we look at this kind of above equation. So refractive index, and this is roughly how things can be seen to happen when we have the x-axis as a frequency. So refractive index n essentially grows when the frequency omega grows. And this is known as a normal dispersion. And this is what happens when we don't have resonances that the nearby the wavelengths of interests or frequencies of interest. And when we would happen to be when we would happen to be nearby resonances, so omega naughts, then the refractive index grows first, as we can see in the figure, and then it actually decreases. And this is the decrease of the refractive index as a function of increasing frequency is known as anomalous dispersion. And this is something that doesn't happen that often in materials because we need to be close by to a resonance for this to take place. And that's why it's called anomalous and not normal. This is what happens. And essentially, please remember this curve going upwards. This is known as the normal dispersion, so that the refractive index grows larger when we are increasing the frequency. So essentially when we are decreasing the wavelength. And then there are also these regions of known as anomalous dispersion. In many times in terms of applications, this is actually very important, so that we even need to have this kind of dispersion in the refractive index profile of our ideal material to make things work in terms of applications. Okay, and then final slide. In optics, we're really interested in most of the time in transparent materials. So essentially dielectric materials. And this means that we are in particular, since we are in optics, that we want to look into the wavelength regime of 380 nanometers to 780 nanometers. And here, dielectric materials are nice because they don't really have electronic states that can be excited optically. So dielectric materials are such that they have an electronic band gap that is of a considerable size, and that essentially means that we cannot excite electronic states using visible light. And then this notion in the framework of the Lorentz model we have just come up with is that we do not really have those resonances in the material, so that the electrons don't really oscillate much when you're looking at dielectric materials and we are exciting them at optical wavelengths. And then subsequently, what kind of dispersion we will have for the material, and this is for the dielectric materials, is that then essentially it's the electronic transitions in the dielectric materials that can be excited are in the UV range. So only at the very short wavelength range we have electronic transitions, and only there we will have those resonances and anomalous dispersion. And when we are at the optical wavelengths, so at the wavelengths around 400 nanometers to 800 nanometers, the dispersion is just normally dispersive, and then the refractive index amplitude will be of the order of ranging from 1.3 to, let's say, 1.8 or so. So we do not go into values of the refractive index being 2.5 or 3.5 as in the case of a silicon. So dispersion of the refractive index is normal at the visible regime, and this is a good rule of thumb for dielectric materials. There's no essentially anomalies that are caused by resonances, so no anomalous dispersion takes place, and then the refractive indices are also quite small, so somewhere between unity and 2, and this is like something that is quite different from the refractive indices of semiconductors that range between the 2 and 4. And this is what I wanted to say. I was able to do it in less than 50 minutes. I'm pretty happy. This is an important lecture, or at least the topics that I have introduced to you are very important. So please pay attention and be familiar with these, because understanding where the refractive index arises and what is the difference between an optical response of a dielectric material versus semiconductor material is highly important. And finally, the dispersion of refractive index is highly important in applications in practice. So you should familiarize yourself with the physical origins. How come we have dispersion in our refractive index profiles? So I thank you now for your time and huge patience of bearing with me 50 minutes. So please enjoy your day. And congratulate you for just sitting still this long with me. Or maybe you were just walking in a forest and listening to me with earbuds. That would have been way better, I think. Okay, so thank you for your time and patience, and please stay tuned. Soon we will have the final lecture on this chapter. Thanks and bye-bye.